Hello everyone. Previous lecture we have studied the concept related with the polar coordinates. In today's lecture we go with new concept and is for solution of a triangle. Very interesting concept it is, and to define this concept we consider one triangle. Okay, here we consider triangle ABC. ABC. Okay, in this triangle we have three sides and we have three angles. Here sides are AB, BC and AC, and angles are, here angle is at A, angle is at B, angle is at C. So in this triangle we have three sides and three angles, and these three sides and these three angles are the elements of the triangle. Now to find solution of a triangle means here by using known elements we find unknown elements. If we have certain set of three elements and in that one is a side, then we find remaining elements. So remember this point. Okay, now in this triangle ABC we define the sides of the triangle. Okay, here side opposite to the angle A is BC and we consider length of this BC as A. Next, here side opposite to the angle B is AC and here length of AC is B. Next, here side opposite to the angle C is AB and here length of the AB is small c. Remember, here to define the length of the sides we consider small letters. Okay, here A, B, C. And to define the angles we consider capital letters, that is here capital A, capital B and capital C. Okay, so by using this concept we define the solution of the triangle. Okay, now in today's lecture we are going to see the relation in between elements of the triangle. Let's go with first relation, and this relation is for the sine rule. Okay, let's go with first rule and it's for sine rule. Okay, now here in sine rule, to define the sine rule we consider triangle ABC. In triangle ABC, here A upon sine A is equal to B upon sine B is equal to C upon sine C and is equal to twice R, where R is circumradius of triangle. Okay, circumradius of the triangle. Okay, now we have to prove this concept for the sine rule, and to prove this we consider one figure. Again we consider one triangle ABC like this. This is our triangle ABC. Okay, here we consider length of the sides. Firstly we see here length of the side opposite to the angle A is small a. Then length of the side opposite to the angle B is small b. Then length of side AB opposite to the angle C is here small c. Here ABC are the length of the sides. Now to prove this relation here we consider one perpendicular drawn from this point A to the BC. Okay, here like this, AD is a perpendicular. Let us consider this point is D. Okay, here AD is perpendicular to BC. Okay, let AD is perpendicular to BC. Okay, now we consider one triangle. Here triangle ADC, we know it is right angled triangle. We define sine C here. Therefore, here sine C is equal to, we know to define the sine C, we consider opposite side. Here in this triangle, opposite side is AD for this angle C. So AD upon here hypotenuse is AC, and we know length of this hypotenuse is B. Here I write this AD separately. Therefore, here AD is equal to B into sine C. Okay, we get this important relation. Now we consider this triangle ABC, and in that we consider area of the triangle ABC. Okay, in triangle ABC, area of triangle ABC is equal to, we know this area is 1 upon 2 into base. Here base is BC, okay, into here height. Height is AD, okay. For height we consider AD, so into AD. This is equal to here 1 upon 2 into, we know length of the BC is A, so we replace BC by using A, into here for AD we define B sine C, okay. So here B sine C. Here again I write this as 2 times area of triangle ABC is equal to here only AB sine C. AB sine C. We get this relation. Similarly, we can prove, we prove 2 times area of triangle ABC is equal to BC into sine A, and 2 times area of triangle ABC is equal to AC into sine B. Similarly, we prove these two. Okay. Now here in this 3 relation, LHS is same. If LHS is same, then RHS is also same. Okay. Therefore, here I write AB into sine C is equal to, then in second given BC into sine A is equal to, then in third given AC into sine B. Okay, we get this relation. Now, what we have to prove? We have to prove, firstly, here A upon sine A is equal to B upon sine B is equal to C upon sine C. And to get this, we divide here each by A into B into C. Okay? Therefore, here A, B into sine C, this divided by A, B, C is equal to, then BC into sine A, this divided by A into B into C is equal to, then in last, here AC into sine B, this whole divided by here A into B into C. Now in next step, here A and A, B and B are cancelled, and here only remains sine C upon C is equal to, then in second B and B, C and C are cancelled, then we get here sine A upon A is equal to, here in last A and A, C and C are cancelled, then only remains here sine B upon B. We get this relation. Okay, now we rearrange this as, here we consider sine A upon A first. Therefore, sine A upon A is equal to, then we consider sine B upon B. Sine B upon B is equal to, then in last we consider sine C upon C. Okay, so we get this relation. Now what we want? We want A upon sine A is equal to B upon sine B is equal to C upon sine C. So I write this as, here A upon sine A is equal to B upon sine B is equal to C upon sine C. Let's denote this as 1. We denote this as 1. Now we have to prove this ratio is equal to twice R. This ratio is equal to twice R. And to prove this, we consider another figure. Okay, we consider one circle, and in that we consider one triangle. Okay, let us consider this triangle is here A, B, C. Here center is at origin O. Okay, so in this triangle, everyone knows here side opposite to the angle A is small a, side opposite to the angle B is small b, side opposite to the angle C is small c. Okay, we get this. Now everyone knows here sum of the angles of the triangle is of 180 degree. Everyone knows this. Okay, then we consider one case here. At least one of the triangle is not of 90 degree, is not a right angle. Okay, suppose here A is not right angle. Okay, here I write suppose A is not right angle. A is not right angle. Okay, now this from point A, we draw a diameter. To define our relation, we draw a diameter like this. Okay, here another point on this diameter is P. Let us consider this as P. Then we join here P and C. Okay, now we know one important relation. Here angle subtended on a semicircle is always a right angle. So here angle is at C is of 90 degree. Is at C is of 90 degree. Now here this AP is the diameter. So we consider twice R for this diameter. Twice R for this diameter. Okay, now here everyone knows this ACP is the right angle triangle. Okay, so here we consider two angles. Here measure of angle ABC and measure of angle APC are inscribed on the same arc. Are inscribed on the same arc. Therefore we get here measure of angle ABC is equal to measure of angle here APC. If we get this relation, here I write sine B is equal to sine P. Sine B is equal to sine P. Now we define this sine P by using the triangle here ACP. Okay, here in triangle ACP, sine P is equal to define the sine P, we consider opposite side. Here length of the opposite side is B upon here hypotenuse is AP. Hypotenuse is AP. Here I write AP is equal to B upon, we know this AP is having twice R, having length twice R, so B upon twice R. Okay, now in next step, here we know sine B is equal to sine P. We know this sine P is B upon twice R. So we get here sine B is equal to B upon twice R. By using this relation, here I write B upon sine B is equal to twice R. Let's denote this as 2. Okay, now we know relation here A upon sine A is equal to B upon sine B is equal to C upon sine C, and in that B upon sine B is twice R. So from 1 and 2 here we get here A upon sine A is equal to B upon sine B is equal to C upon sine C and is equal to twice R. So this is the very important relation in between the elements of the triangle, and we consider this as sine rule since sine is used in this relation. Okay, so very interesting part and very important part it is. Now by using this relation we get one another relation. Okay, let us consider remark for this. Remark. Okay, if we have this type of relation, here I write A separately as, okay, again I write this as we consider A upon sine A is equal to B upon sine B is equal to C upon sine C is equal to twice R. Okay, here A is equal to if we compare or if we equate this first with twice R, we get A as here twice R sine A. Then if we equate this second with twice R, we get B is equal to twice R sine B. And if we compare or if we equate this third with twice R, we get C is equal to twice R sine C. This is also very important part. Try to remember this relation. A is equal to twice R sine A, B is equal to twice R sine B, C is equal to twice R sine C. Okay, so this is all about the rule, sine rule, and in that we consider the relation in between the elements. Okay, now we go with our second relation. We consider the second relation as for cosine rule. Okay, let's go with our cosine rule. Cosine rule. Again, to define the cosine rule, we consider triangle ABC. In triangle ABC, we have three type of relations. Okay, let's go with first one. A square is equal to B square plus C square minus 2BC into cos A is the first one. Second, here b square is equal to a square plus c square minus 2 times ac into cos b. Third one, here in third we consider c square is equal to a square plus b square minus 2 times a b into cos c. So related with this cosine rule, we have 3 type of relations. We have 3 type of relations, okay, and we have to prove this relation. Again, to prove this relation, we consider one triangle. Okay. This is our triangle ABC. Let us consider origin is at A. Okay. We consider origin is at A. Then we consider B here on x-axis. Then here this is our point C. Remember again here A is at origin, then this AB is along x-axis and we consider point C here. Okay. So here we consider length of the sides again. Everyone knows here length of the side opposite to the angle A is small a. Then length of the side opposite to the angle B is small b. Then length of the side opposite to the angle C is small c. Okay. Here coordinates of, we consider coordinates of point A, B, C as here since A is at origin we consider here 0, 0. Then we consider here B and is equivalent to here C 0 since length of AB is C and is along x-axis, so we consider C first and then 0. And in last here C, here for C we consider B cos A, B sine A. So these are the coordinates for the given points and we have to prove this relation now. We have to prove this relation now. Let's prove our first one. Let's prove this first one. Okay. To prove here in first given a square is equal to b square plus c square minus 2bc into cos a. Okay. We have to prove this relation. Let us consider LHS of given things. Here LHS is equal to a square is equal to, we know here A is the length of the side BC. I repeat again, here A is the length of the side BC. So I write here BC square. Now by using the distance formula, here I write BC square as, now everyone knows the distance formula. Okay. So here given coordinates of BR, I repeat, here coordinates of BR C0 and here coordinates of CR B cos A, B sine A. By using distance formula, here I write C minus B cos A, this bracket square, plus in second bracket here 0 is given, so 0 minus here second is b sine a, this bracket square. Now we consider expansion of this square. Okay, here I write this as c square minus 2 times bc into cos a plus here b cos a bracket square is what? Is a b square cos square a. Remember, here c minus b cos a bracket square is in the form a minus b bracket square. And we know a minus b bracket square is a square minus twice ab plus b square. Similarly, here we consider the expansion. Now in the next, plus here minus b sine a bracket square is b square into sine square a. Okay, this is equal to, here I write okay, here c square in first as it is, then from this third and from this fourth, here we take b square common. Okay, so b square into bracket, here we have cos square a plus sine square a, next minus 2bc into cos a as it is. This is equal to, here c square plus b square into, we know cos square a plus sine square a is 1, then minus 2bc into cos a as it is. And lastly, here we get c square plus b square minus 2bc into cos a. And this is our RHS. This is our RHS. Okay. Similarly, we can prove another two cases. Okay. Here one part we prove one part, and here similarly we prove second and third point. So this is for here the cosine rule. Here for the cosine rule. Okay, here also in the cosine rule we prove or we consider the relation in between the elements of the triangle. Okay, here now we know the relation, these three type of relation in the cosine rule. We consider some remarks related with this cosine rule. Okay, let us consider our first point. Let us consider our first point. Here we write this cos a separately as, by using first we write cos a separately as, here b square plus c square minus a square upon 2bc. This is by using our first relation. Similarly, here I write cos b separately as, consider the second one. Here I write cos b separately as a square plus c square minus b square upon twice a c. And in last, here I write cos c separately by using this third relation as a square plus b square minus c square upon here twice a b. Remember this point also. Remember this point also. So this is all about our two rule. First is sine rule and second is cosine rule. In next lecture, we see the proof of cosine rule and examples related with sine rule, cosine rule and the projection rule. Thank you.